Ladies and gentlemen, class recording has started. So, let's get rid of this over here. There we go. Okay. All right. Over the past couple of days, we have been looking at the relationship between these two things, velocity and acceleration. And then, over the past couple of days, we've also thrown in displacement as well. And talking about how the acceleration changes the velocity, and then using the velocity to find out how far something goes if we know the time that it's accelerating. We started off with this, right, non-accelerated motion, where the acceleration is equal to 0. We said that that requires what? If it's non-accelerated motion, what has to be true? Constant velocity. No. If it's constant velocity, it can't be no acceleration. So it can't be getting faster, going slower, or changing direction. None of those things. And we can tell this is constant velocity because our pictures, right, nice regularly spaced intervals. It keeps going the same distance each second, which is different than this ramp, right, where the intervals, the spacing on the pictures keeps increasing. If that's 1 second worth of time and the pictures keep getting farther apart, that means it's going farther each second. If it goes farther each second, that means it's going faster. We showed that here down at the bottom with the nice gradual increase in velocity, right? Velocity increases from 0 to 2, 2 to 4, 4 to 6, 6 to 8, right? A nice gradual increase because the acceleration is 2. This equation represents that nice gradual increase, right, based on what the acceleration is and what the initial velocity was. It just so happens on this ramp, the initial velocity is 0, so we just multiply the acceleration by whatever time we're looking for. But then we also used these two equations to figure out how far something has gone, even though it keeps getting faster and faster and faster. We can tell from the pictures that it keeps going farther during each second interval, but exactly how much farther, we need to use these two equations. Okay? Good there. Yesterday, we introduced the idea of free fall. Free fall is a fancy name for what? Uniform acceleration caused by what? Gravity, right? Where gravity and gravity only are causing the acceleration. Here on Earth, our free fall acceleration is around 10 meters per second squared, meaning that if something experiences an acceleration of 10 meters per second squared, what's going to happen to it? If something is experiencing and accelerating, or it's accelerating at 10 meters per second squared, what's going to happen to it? Let's go more generally, not just that it's getting faster, but its velocity is going to increase. Let's not just go increase. More generally, it could change by 10 meters per second, right? If something starts at rest, then yeah, the velocity is going to keep increasing by 10 meters per second for every second that goes by. That's what the speedometers are telling us in these pictures, right? It goes from 0 to 10 to 20 to 30, okay? But how far it goes keeps increasing as well because it keeps going faster. Good with this so far? It's all review. All right. Let's start today with page 3 of your packet. At the top, it says free fall speed. Now, we're trying to use an analogy to explain what gravity does to things. So stick with the analogy at the beginning, and then we'll hopefully transition more into what's actually happening. Okay? So, question number 1. First, you guys need an Ant Mini, because Ant Mini gives you $10 per second for 4 seconds. So Ant Mini just hands out tens. No one asks what rich Ant Mini does. No one asked how she got her money. You know, maybe Maybe her first husband died under mysterious circumstances. Who knows? You know, like, so. You could just look at Aunt Minnie. You could tell what she does.
Look at that smile.
So.
You can tell what she does.
Ask Kelly. She brought it up. This is all right. This is inappropriate for school. Like that's, and we're recording it. So great. Now it's out there for everybody to see. All right. So Aunt Minnie says, Aunt Minnie gives you $10 per second for 4 seconds. I think most of us could probably come to the conclusion that after 4 seconds, how much money are you going to have? $40. All right. Question number 2. It says, a ball dropped from rest picks up speed at 10 meters per second. Just like acceleration of gravity, right? Free fall acceleration here on Earth. So if it's falling for 4 seconds, how fast is it going to be going? Okay? Just like we did yesterday, right? If something starts from rest and it gains 10 meters per second for every second, after 4 seconds, 40 meters per second. Okay? All right, next. Not Aunt Harry, Uncle Harry. So it says, you have $20 now. Maybe it's her second husband. Yes. So he used to be her gardener, but then they got married. And, so. Wow. So that's what Aunt Minnie does. She's a science teacher. Because we make so much money that we can afford to hand out $10 a second to people. Just for seconds. All right, you have $20. Uncle Harry gives you $10 each second for 3 seconds. How much money are you going to have? No, not this part. No, absolutely not. All right. Number 4 says a ball is thrown straight down with an initial speed of 20 meters per second. After 3 seconds, how fast is it going? Making an analogy between the Uncle Harry example in number 3 and number 4, you might be able to make an educated guess about how fast the object is going. Okay. The correct answer here is going to be 50 meters per second. Okay? So, let's talk, right? Gravity changes the velocity of an object by 10 meters per second for every second. Right? Does that are we good with that? At least that we've talked that, right? That's what acceleration is, a change in velocity. Gravity changes the velocity by 10 meters per second for every second. Good? Gravity on Earth, I should say. That is true regardless of whether we just drop an object or whether we start it throwing it downward or if we throw it up in the air. Okay? The velocity is going to change by 10 meters per second for every second. Okay? Example number 1 and example number 3 with Aunt Minnie and Uncle Harry. Right? In Aunt Minnie's case, you didn't start with any money. But how much money were you gaining? Well, you gained 40 ultimately, but you were getting 10 a second. In Uncle Harry's case, you started with $20, but how much money were you gaining? You were still gaining $10 a second, regardless of the fact of whether you started with 20 or not. Does that make sense? So is the case with acceleration, or acceleration caused by gravity. Whether you start at rest or you're already moving, you're still going to pick up speed. Remember this equation? Hopefully. Does that look familiar? We talked about it the very first day, and I've shown it to you the last 3 days in a row. Okay. This tells us the relationship between how fast you're going to end up going based on how fast you were going and what the acceleration is. All the examples that we've done up until this point, what was our initial velocity? In all the examples we've done up until this point, what was the initial velocity? 0. So all you had to do was take the acceleration and multiply it by the time. But in this case, when gravity started pulling on the object, it was already moving at 20 meters per second. So in this case, VI is what? 20. Okay? Does that make sense?
Yeah.
Yeah. Because you threw it with an initial speed of 20, right? Why is this 10? Because that's the acceleration caused by what? That's how much gravity is changing the velocity. How long does that take? 3 seconds. You solve this equation, what do you end up with? 50. Okay. Good there. Well, yeah, but we talked about the idea that on Earth, let's just round it to 10 because that makes our calculations a lot easier to do. Okay? Technically, you could plug 9.81 in there and get a more exact answer, but for our purposes, 10 that makes the math a lot easier to do. And it's close enough. All right. Apparently, your mom has gotten wind of the fact that Aunt Minnie is just handing out $10 bills a second. Okay? So, you have $50, but your mom makes you pay back Aunt Minnie at $10 a second. Because your mom doesn't believe in taking old ladies' money, apparently. All right?
Aunt Minnie gave
I don't know what her problem is, but, you know, whatever. So,
it's just crazy Aunt Minnie.
yeah. So if you have to pay back $10 every second, and you have $50, how long is it going to take for you to get to 0? 5 seconds. Okay?
Why would she make you like wait and be like, here, wait,
Yeah.
here?
What? Because it's bad, right? You're losing money, right?
But again, why would your mom be like, wait a second?
Yeah, and you're down because you're giving $50 away. So, all right, now, are we at least okay with this for beginners?
Yeah.
Okay. Let's take a look now at questions 6, 7, and 8. Okay. Okay. So here's my picture that shows first, make sure, okay, as a public service announcement, you should not try this at home. Okay, you should not shoot an arrow straight up into the air because arrows that get shot straight up in the air, guess what happens to them? They come back down.
Right in your foot, like you grown-ups do.
I am very proud to say I would not know that. So
You ever watched it grown up?
I've heard that is a terrible movie.
That is the funniest movie ever. You have to watch it.
All right, so let's talk. Okay. Before we answer these 3 questions, I'm going to add some detail to this drawing. Okay? You have the drawing there. You might not have enough room to add as much detail as I'm going to add, but, sorry. All right. I'm going to draw on this picture representing where the arrow is, okay? But instead of drawing arrows, I'm just going to draw a little dot because that's easier to draw than drawing an arrow. Okay? Less, it takes up less space. How's that?
Yeah.
Okay. So here we are, right after the arrow has left the bow. So it says you shoot an arrow straight up at 50 meters per second. So this is the exact moment when the arrow has left the bow, and now that the bow isn't shooting it up anymore, what's acting on it? Gravity. It tells you in the problem that here we're going 50 meters per second. Okay? This is 1 second after you shot the arrow. Okay? We know that the free fall acceleration, or the acceleration caused by gravity here on Earth, is how much? 10. And that means that the velocity has to change by 10. But in this case, if the arrow is going upward, which way is gravity pulling on it? Downward. So when we say that the velocity changes by 10, specifically it's going to do what here? It's going to decrease. So after 1 second, now the arrow is only going 40 meters per second. That's the next second. Gravity causes the velocity to change by how much? 10. So it's going to only be going now 30 meters per second. Okay? Next second, how fast will it be going? Hold on, relax. All right, our first, are we okay with these dots and these numbers?
Yes.
Okay. Okay, good. Good. So, the last velocity that we've written on this chart here is what? 0, meaning what has happened to the arrow eventually? It has stopped, right? That's as high as it's going to go. Because, right, if it stopped, it's not going anymore. Okay? So for question number 6, it says you shoot an arrow straight up at 50 meters per second. When will it, quote, run out of speed? How long does it take the gravity here on Earth to take something from 50 to 0? It takes 5 seconds. Right. And we've kind of already, that's a bad S, so 5 seconds.
Oh, okay, now I see.
SEC. And we've kind of already talked about the answer to number 7, right? After that 5 seconds, what's the speed going to be? Okay. All right. Yeah, very similar, right? Because as the speed is getting smaller, the height is getting bigger, right? Okay. Another thing, right, to bring it back to some things that we talked about earlier this week, or maybe even on Friday, right? What do we see about the spacing between the dots? It keeps getting smaller, right? Like we talked about this, I think, if we rolled something up the ramp, we would see those spaces getting smaller and smaller and smaller instead of getting bigger and bigger and bigger. However, at this point in the picture, this object is at rest up in the air. Is gravity still acting on it?
Yes.
Yes. If something isn't moving, but gravity is still acting on it, what is it going to start to do? It's going to start going down. And so here, right? So, Amanda, what time are we going to be talking about here? What time are we going to... So this is going to be t equals 6, right? And then the speed will be 10. Okay? And then, after 7 seconds, the speed will be 20. Okay? Hey, how long will it take to get back to where we shot it from?
10 seconds.
It'll take 10 seconds. It took 5 to go up. It'll take 5 to go down. How fast will it be going?
Wait, but that depends on if you shoot it directly up.
That's true. We're talking about something going straight up in the air.
And then no wind.
Okay? Actually, no wind is the important part. Whether we shoot it straight up in the air or not, that doesn't matter.
Okay,
But if
it'll be the
it's,
same. It'll be the same.
this will be on the quiz tomorrow, but we got more to do.
Wait,
Okay?
is it partner quiz? It's
Okay.
partner quiz.
Doing good. Hey, it depends on what we're asking for. Okay? This question here is only asking you about what? Speed instead of velocity. If it was asking about velocity, these would be minus 10, minus 20, and minus 50. That's going to be important in just a second here. Okay? All right. First, are we okay? Well, sorry, we should answer. So what will the speed be 6 seconds after we shot it?
10 meters per second.
10 meters per second. And then 7 seconds after we shot it? 20 meters per second. Okay. Good with that so far?
Can you find out like how far it is?
Hey, Kenny, see what the next set of questions says right above it? What? Relax. All right, so let's do this. Okay. I'm going to not do that. I'm going to move this all out of the way. No. Oh my goodness, that is not what I wanted to do. Oh, that is apparently. Come on.
Did?
It's alright, we'll go with it. I could. I can do this too. Alright. Apparently that didn't work. Alright. Okay. So, Kenny, let's talk about what you were just asking about. Okay. So, the next set of questions down at the bottom still relates to this picture. Disregard this picture. Okay. But, like it says, speed is one thing, distance another. Where is the arrow that you shoot up at 50 meters per second when it runs out of speed? So in this example, for question number 1 here, it's asking about the trip from here, or actually from here to here. Okay? All right. This still applies. Even though we're slowing down, that relationship for velocity still applies. Okay? What are we trying? What is this question asking us for in this equation? Not the displacement over time. If it's just asking us for where, it's asking us for the position or the displacement. It wants to know this, right? How far away from the starting point is the arrow when it reaches the top? That's what it's asking you for. So, that's our unknown. Now we have to fill in the rest of the equation. Time-wise, how long did we say it took to get from the bottom to the top? 5 seconds. So we can plug in 5 right here. Okay? The average velocity for this trip is starts at 50, ends at 0. So the average is 25. Okay? Solve this equation. Right? We're talking about the whole trip, right? If we solve this equation for x, right? 125 meters. That's completely unrealistic, by the way. You can't shoot an arrow at 50 meters per second.
Isn't that really slow?
No, it's pretty fast.
Oh,
It goes,
feet per second.
yeah. If you go, that's 50 of these every second. So, go ahead.
So that 125 was going from where you first shot it all the way to the top. So that's the average velocity.
That's the displacement. That's
Oh, the average velocity is 25.
the average velocity is 25 because for this trip we started at 50 and ended at 0, so the average is right in the middle, right? But it took 5 seconds to do that. That's why we're multiplying that by, okay? All right, now, there are 2 ways that you can answer question number 2, okay? Because you guys jumped ahead, which was good, by the way, and you realized that these technically should be negative because they're velocities, let's use that to answer question number 7. So question number 7 says, how high will the arrow be 7 seconds after being shot in the air? So in that 7 seconds, this arrow goes up and then comes back down to here. To answer question number 7, we need to know that. Okay? Sorry, question number 2. Sorry. All right? So there's 2 ways we can do it. Okay? That's one way. Let's go with this first. Okay? This equation still holds true even though we've gone up and we've come back down. Okay? Remember, displacement is how far away you are from where you started. Yes? That sound familiar? So this highlighted section, what we're trying to find, right? That's the displacement of the arrow, because that's how far away we are from where we started. Okay? We're still trying to find the displacement, so now we have to plug in the other numbers. Okay? Even though we've gone up and started coming back down, how much time does this trip take? 7 seconds. So 7's going to go here. Okay? Now, not 50 minus 20. When we take the average of something, we add them together and then divide by 2. It just so happens in this problem, one of the things we're adding is positive, and the other thing that we're adding is negative. So the average here is 15. We did 50 minus 20 because we really did 50, but really we did 50 plus negative 20. Mathematically that's the same thing, but technically if we're staying with what we've done up until this point, we did 50 plus negative 20, because that's how we find the average. Because these numbers here, this equation, right? Sorry, people who are watching at home, I should. This equation includes average velocity, not average speed. Those are two different things. Okay? Because velocity in direction is important. Okay? So, technically, the overall average velocity is lower than it was on just the up trip, because now we have a little bit of the down trip that we have to factor in. Okay. The other thing so, what's the displacement after 10 seconds, Eddie? Zero, because you end up right back where you started. Okay? Well, then you're not only under the influence of gravity anymore, and these numbers don't hold true. All right. The other thing we could do, the other thing that you could do, you know that it's 125 meters up. Okay? If you want to, you could just figure out this little section right here, okay, and subtract from 125. Does that make sense? Okay? You could do that, or you could just take it all as one big trip. It should get you the same answer. Okay? Good there. Let's go to the back page. I know there's a couple questions down there at the bottom. I'm not going to worry about those questions right now. Average speed is 15.
Yeah.
Distance is 45.
Water surface is 45.
Yes. Because it's 15 times 2.
Oh, 3 seconds. Okay. Then the first one is 30, right?
The average speed is 15 over those 3 seconds. Because it's 0 to 30
And it falls
divided by 2.
in 3 seconds. How fast is it when it hits?
Oh, when it hits, it'll be 30.
Yeah.
All right. On the back page, you have 3 charts and you have 2 pictures. Okay? We're not going to do the third chart. We're just going to do chart 1 and 2. Okay? Chart number 1 relates to this picture, which is the one on yours that is closer to the top. Okay? The chart number 1 goes along with this picture right here. They look similar, but they're different. Okay? All right. Chart number 1 gives you time and velocity for this ball that was thrown into the air. The first picture that shows up is always time equals 0, because that's the moment that the object has left the person's hand and is now being acted on by gravity and gravity only. It tells you here that the velocity at that point in time is 30 meters per second. Okay? That makes sense? T equals 2, even if it oh, sorry, not T equals 2, my bad. T equals 1, even if it didn't tell you in the chart, what should the velocity of that object be there? Should go down by 10, because that's what gravity does, right? T equals 2 here. T equals 3 here. Okay? Good there? And then 4, 5, 6. Okay? And it gives you the velocities as -10, -20, -30. Okay? I'm going to change something in this chart. Here, where it says distance, I'm going to change that to say displacement. Okay? So, Johnny, before we fill anything else in. What's the displacement after 6 seconds? Okay. The displacement of this object after 6 seconds is going to be 0. Because after 6 seconds, where does it end back up? Right back where it started. Okay. Now, it doesn't stay there, but that's where it, so
It's like on the same level. But
Right.
Like the same.
right, so it would do this, right? It would be like this.
Whoa.
When it gets back to this height, even though I don't catch it, the displacement still would be 0, right? Go to you, go ahead. Okay. As far as displacement and direction goes, okay, up until this point, it's always above where it started, right? Once it gets past here, now it's below where it started, okay? So even though on this down trip over here, the velocities are negative because it's traveling downward, we're still above where you started, so those displacements will be positive. Displacement won't end up being negative until you get here. Does that make sense? Because displacement tells you where, and velocity tells you what. You can be on the positive side of something, but traveling in the negative direction. Okay?
So like at 7 seconds, when it's 40, -40, then it would be
I'll tell you this.
become negative.
I'll tell you that's the answer to that one. Okay?
Oh, wait, what? Like in the cliff and like what happened?
No, it doesn't hit the cliff. So, see that one that I put the bubble around? Figure that one out. You can talk to the person next to you. Go.
Oh, it's 0, it's Oh, yeah, yeah. Wait, no, I thought it was 30.
It's not 45, you can.
It's 60.
What's 15 times 3?
Why you got 15 on 3?
Think about it.
You're doing the average?
I did it, Flippy. What did you do?
Angel, I was at your house.
Sure.
I suppose, if you looked at it that way.
How many places?
Good.
Wait, why are we using the average?
Oh. Oh.
What's that? Average.
right. So.
I got this. I feel it.
All right. Okay. First, let's talk about just the part that I put the bubble around. Okay? From here to here. Right? During that interval, the average, right? This still holds true. Okay? The average velocity during that trip, up trip, starts at 30, ends at 0. The average velocity is going to be what? 15. We're trying to find the displacement. How much time are we talking about? It takes 3 seconds to get to the top. Solve for x, 45.
You just like add 10 and 0.
You could add, if you want to, you could add up those individual ones if you would like.
10 and 0 is 5 divided by 2. I mean, 10 and 0 is 10 divided by 2 is 5, and then add 5 on the 40.
Yeah, like you could figure out each individual interval and add them all together. That's fine. Or you could do it once. All right. So here's what we'll do. Okay. Tonight, don't forget, there's a couple of attachments, a couple of files on that homework assignment that are similar to these problems. Okay. Try them. Answers are posted. Tomorrow in class, we'll go through table number 2. Okay? And that will be sort of our review, and then we'll take the quiz the last half of the period. Okay? Quiz is open notes, and you'll also get to work in small group. Okay? All right. Good job today, everybody.